Sample exam 4 of 8, problem number 43. Suppose n sticks, each of length 10 units, are broken into 2 pieces at random. If xi is the longer piece and yi is the shorter from the ith stick, I equal 1 to n, what is the correlation coefficient among the pairs x1, y1 through xn, yn? Problem number 43. We're given that we have a stick that's 10 units, we break it in a random spot, and then we let x be the largest and y be the smallest. So this is a picture of what's going on. Wherever we break it, there's an x, and then the y value, or the other half, both those have to add to 10, which is they're all on this diagonal line. No matter where we break it, they're going to be on this. It's a perfect line. So our correlation should be -1. But now let's prove that. So as we said earlier, this is a y, which is 10 minus x. So x and y sum to 10. And then if we add up all our data points, so add up the 10, the n sticks, it's going to be 10n. Well, then we can take that sum into each of those and divide by n, and we get x bar plus y bar is equal to 10. And that's going to play a part in our calculation below. So here's our formula for r. And we're going to mess with these yi minus y bars right here. And we know that yi is equal to 10 minus x, which is this value here. And minus y bar is going to be x bar minus 10, which is this. Well, the 10s cancel, and then that leaves x bar minus yi. But if we take out a -1, then it's xi minus x bar. And so then this becomes squared times a -1, which you factor out, which is this. And then on the bottom, you can do the same thing, that this y bar, yi minus y bar, can be shown to be this. And since it's squared, it doesn't matter if we factor out a -1 or not. So you have 2 of these quantities, square root, so you get 1 of them. Well, then those cancel, leaving -1 as your answer. Number 44, suppose x1 through x6 and y1 through y10 are 16 independent normal random variables, all with unknown mean mu. Suppose that each xi has a variance of sigma sub x squared, and each yi has a variance of sigma squared sub y. If sx squared and sy squared are the usual unbiased estimators of sigma x squared and sigma y squared, respectively, then this probability is closest to. So problem number 44, a little background first, is that this quantity here is chi-squared 5. So notice that in sx squared we're dividing by 5, which is 6 minus 1. And we have to get rid of that. So that's what the 5 is. In the same way, this is a chi-squared 9. Well, when you're developing an f-test, then you need to divide, it's a chi-squared divided by its degrees of freedom. But in the sy squared, we're dividing by 5, or 9 in this case, which is the degrees of freedom. So we don't need the multiple out front goes away because it's divided by its degrees of freedom already. And then we know that the variance that we're trying to estimate is 2x squared. And then this here is sx squared divided by chi squared. Now divided by the degrees of freedom, which is in our unbiased estimate here. So then that simplifies to this, which is chi squared, which is f, 9 numerator and 5 denominator degrees of freedom. But since we could flip those, take the reciprocal, which is this, and then we reverse the numerator and denominator degrees of freedom, 5 and 9. And the reason I do that, it depends upon what kind of table you're given to look these up. So we want to find the probability that 3sy squared is greater than sx squared. So if you divide the sx squared over and the 3 over, we get this. Well, this isn't quite an f, so we have to divide by 2 on both sides, which is this. And then, so that's an f 9 and 5 degrees of freedom greater than 1/6. And then depending upon what kind of table you have, you may have to take the reciprocal of each of those and remember to change the inequality sign, or it could be an f 5 and 9 less than 6. Either way, you're going to get, it's approximately equal to 0.990. Number 45, let x and y be joint normal random variables with common mean 0, common variance 1, and covariance 1/2. Which of the following is equal to the probability that x plus y is less than or equal to the square root of 3? So problem number 45, little background first. If we know that x and y are jointly normal, common mean 0, variance 1, covariance 1/2, then the linear combination is normal. And so we just find expected value, which is 0, and the variance of it, which ends up being 3. So x plus y is a normal mean 0 and variance 3. So to find this probability that x plus y is less than or equal to square root of 3, if we subtract the mean of both sides, which is 0, and divide by the standard deviation, which is the square root of 3, then this becomes a z. And then since we divide it by the square root of 3, we get this. Well, this is probability that z is less than or equal to 1, which is 0.84. Problem number 46. Let x be the number of independent trials required to obtain a success where p is the probability of success on each trial. The null hypothesis that p is equal to 0.1 is to be tested against the alternative hypothesis that p is equal to 0.3. The null hypothesis is rejected if x is less than or equal to 4. What is the power of the test if h1 is true? So problem 46 is we are given this, that we're going to repeat a trial until we have a success. So the density for it is this, where x is 1, 2, 3, etc. And we want to find the probability that x is less than or equal to 4 under the null hypothesis, which is h1. So this is the power of the test. So then we plug in, when x is 0, we get this. If x were 1, we get this. 2. It's actually 4, 3, 2, 1, because we can't have 0. So 1, 2, 3, 4. And there's a p common in both of those, so you can factor it out, and you get this. Now, the first time I did it, I just plugged in the values and calculated it and found the answer. So then I had to find the answer, or the values in the answers. They're sort of in a tricky way. So, but I went ahead and solved this in a way, or simplified it in a way to match the answer, but you don't have to do that. Just find the answer and then calculate the answers to see if they match. So I factored out a p, and then this little expression here is a geometric, which can be expressed like this. And then 1 minus p ends up just being p. So that p and this p cancels, leaving the top. And then under the alternative hypothesis, p is 0.3, so this is 0.7, and it equals 1 minus 0.7 to the 4th. Number 47. Suppose y1 is less than y2, which is less than y3. Denote the order statistics of the random sample x1, x2, x3 from a uniform distribution over the interval 0 to 1. Which of the following is true of the conditional distribution of x or from y2 given that y1 is equal to little y1 and y3 is equal to little y3? Okay, so number 47, you can do this in a quick way, and that if you know the distribution of all the order statistics, well, under a uniform distribution, the answer is n factorial. And since we only have a sample of 3, then the joint distribution of all the order statistics is 6. So this is a uniform distribution. So then if you're going to condition on a uniform and then find the value, then you get a uniform back. So the answer is that it's uniform, you know, under the constraints of the condition. And so, and if this were the condition, then you know that y2 has to be between y1 and y3. So you sort of can quickly know that it's a uniform. But let's go ahead and show that. And here the joint order, the joint density for y1 and y3 can be shown to be this. And remember, we're in a assuming that f, or the data, follows a uniform 0, 1 variable. So then this joint, or this conditional, is the joint divided by this conditioned variable. So it's 6 over this, which is 1 over y3 minus y1. Remember that we're given these values, so these are constants. So this is a constant in regard to x2. And you know that x2 has to be between these, so this is a uniform distribution. So the answer is A. Number 48. A uniform density function for x over an interval of unit length is such that the probability that x is between 1/4 and 1/2 is equal to 1/4. What is the left-hand endpoint of the interval of the unit length? Now, number 48, we're given that x is a uniform, you know, from say theta to theta minus 1, and I just put those values there to maybe help solve the problem. But the total distance is 1, and we're also given this probability. So then this is sort of the setting that we're in, and then with this information, can we find out what this left endpoint is? And the answer is no, we can't. So the answer is E. Number 49. Suppose xj is equal to zj minus 1, where j goes from 1 to n, and z sub 0 through z sub n are independent and identically distributed with common variance sigma squared. What is the variance of 1 divided by the sum of the xi? So number 49, we want to find the variance of this sum, but that sum is written as z's, which then when you write it out is the telescoping sum, which reduces to zn minus z0. So when we're finding the variance of 1 over n of the sum of the xi, that ends up being, since that's a constant, it goes out front squared. So we're trying to find the variance of zn minus z0, which is sigma squared, and there's 2 of them. So the answer is 2 sigma squared over n. Problem number 50. Suppose x is a binomial random variable based upon n independent trials, with p being the probability of success on each trial. If the probability that x is equal to n is equal to 0.00032, and the probability that x is equal to n minus 1 is equal to 0.00128 n, what is p? Now problem number 50, we're given a binomial, And we're given that the probability that x is equal to n, which is this in the binomial case, is this. And we're also given that probability of x equal to n minus 1, which the formula is this, is equal to this value, 0.00128n. Well, this n cancels with this n, and then you multiply that in, and you get this is equal to that. Well, Pn is this, so you can plug that value here, take it across, you get here. Then we're left with these two expressions, and if you divide them, you get P, and then you take the values, reduce it down, you get the answer is 0.2.